So, in order to talk more about nuclear reactions, we need to talk about some special and unusual radioactive particles and energy types that we'll see in these reactions. And so, this is where this gets kind of like a fun chapter. We're going to learn about nuclear equations and how to balance them, stuff like that. The alpha, beta, and gamma radiation types are something we mentioned briefly back in Chem 221, I believe it was, and they all correspond to a particle or an energy. So an alpha particle is nothing more than a helium nucleus. Now most helium is helium-4. So you can see the symbols right there. We have a 2 on the bottom by the He and a 4 on top. 2 is the atomic number of helium, and since most helium is helium-4, that's why there's a 4 right there. There is some helium-3 and other things, but most of it's helium-4, so it's a pretty good guess. Now sometimes instead of He, people will use an alpha symbol there. Alpha represents alpha radiation, which is what this is. If you've ever been to a birthday party, and they sometimes have balloons, all right, and if balloons are made with helium a lot of times, so if you kind of suck the helium in, you talk like a chipmunk for a while, ha ha ha, and, that's really great, you're really dumb and wasting brain cells or whatever. However, you wouldn't want to do this with alpha radiation. Alpha radiation is helium, but it's supercharged helium, and it would like bounce around in your body and it would do horrible things. So this isn't the normal version of helium by any means, and that's why sometimes it's given the little alpha symbol. But you can write He as well, and that's no problem. Now, earlier we did see a beta particle. Beta particles are supercharged electrons. So while electrons can turn chlorine into chloride and stuff like that, this as well is like a supercharged beta particle, and you wouldn't want to mess around with this by any means. Now, electrons a lot of times get the symbol E, and you're welcome to use that. You can also use beta, that symbol right there for it. But look at the numbering. It has a 0 for a mass number because it has no protons and neutrons. And for its atomic number, it has -1. And that's a little weird, but for right now, just take it as a leap of faith. There's a reason for it. Kind of crazy. So electrons, 0 minus 1 E, or 0 minus 1 beta. Gamma radiation is pure energy, so there's no mass at all. So there's no atomic numbers, no mass numbers, anything like that. It's literally pure energy. Gamma radiation is one of the electromagnetic radiation types we talked about. It's more powerful than X-rays, pretty powerful stuff. Once in a while, we'll see protons and neutrons as well. We saw, I believe, a problem earlier with a proton. Protons have 1 proton, so the atomic number, lower left, is 1. Protons plus neutrons is equal to 1 as well, so that's why you see the 1-1 symbolism. 1-1p or 1-1h for hydrogen, because that's basically what it is, no problem. And by the way, I should point out here that these particles, again, are supercharged version of their normal counterparts. So all of them will have the electrons stripped away. So the hydrogens and the protons will be positive, the heliums and alpha particles will be positive, but it's not a major energy component, so chemists will usually ignore it. So we usually just leave the upper right-hand corner empty where the charge would go. It's just assumed that the electrons have been stripped off a long time ago, but that's neither here nor there. Now, neutrons have no protons, so the lower left-hand number is 0. Protons plus neutrons would be 0 plus 1, or 1. So 10N is the symbol for the neutron. And finally, the best for last, the wildest of all of these particles is called the positron. And the positron is an anti-electron. Now, if you've ever watched Star Trek and shows like that, they'll talk about antimatter, all right? And antimatter, when it touches regular matter, it explodes, and it's a big thing in a lot of science fiction shows. And I love that kind of stuff, I won't lie. However, antimatter is real. It's a real concept. It's a very difficult form of matter to deal with because if it touches anything that's normal, it explodes. Lots of energy is given off. But positrons do exist. We'll talk more about the positron in a little bit. Notice the nomenclature for the positron versus the electron, the beta particles. They're both E and beta, like the beta particles were, but that lower left-hand number is a positive one, and we'll talk about why that's important here pretty soon. You always want to write positive one. You don't want to write just just one. It's not a proton like in the proton example earlier. It's a positron. And so anyway, it's kind of a wild thing. We'll talk more about antimatter here in a little bit. There have been a lot of advances in antimatter of late, like in the last 10 years or so. And one example that just amazed me shows these two versions of hydrogen. Now, the top picture there shows a proton in hydrogen and the electron around it. That's a normal hydrogen. And it shows some quarks over there on the right. And physicists will go below the protons and electrons to figure out the quark combination, stuff like that. Well, an anti-hydrogen atom has been found, and it's being studied, which is just amazing. So instead of an electron, you have a positron, because that's an anti-electron, and instead of a proton, you have an anti-proton, and you can see that the quarks over there are different. So it's amazing. I mean, you have to have really powerful magnetic fields and stuff to make them, because you don't want them to touch anything. When matter and antimatter combine, it's always bad. But just realize this is a really neat area of physics, and I sure hope there's going to be some cool developments coming down the pipeline.
You're aware that radioactive materials give off energy, especially if we expose this sample to ultraviolet light. We can see it glow. There are three different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation. Here we have a nuclear scaler that measures radioactive decay. Each click that you hear is a nucleus of an atom that is decaying by giving off a radioactive particle. This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler. What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection. Let's place a beta particle in our sampler. We notice that there's a slight increase in the counts. The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. We notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample. We notice immediately that more energy comes from the gamma. 1 sheet of lead and 2 and even 3 that quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles, alpha and beta. Gamma is an electromagnetic energy wave. Well, let's see what happens as we go from being close to a radioactive source to far away. We notice that the amount of radioactivity is greatly decreased by distance.
This is a cool video for several reasons. First of all, it shows that there are 3 types of radioactive sources generally out there, alpha, beta, and gamma. And of the 3, gamma is by far the most powerful. It penetrates things a lot better than beta and alpha. Beta and alpha both have mass. They're both helium and or electrons, which both have some kind of grams. If you have a alpha particle and you throw it, it will bounce off other mass, because that's what mass usually does. Mass bounces off and stuff. But gamma rays will go right on through. So that's why it has the best penetrating power. It's like a wave. It's like a flashlight, all right? The flashlight won't be stopped. It just kind of keeps going. You can silence the radiation with appropriate shielding, though. They used lead there on the beta to effectively shut it down, but the gamma, as you can tell, was a lot stronger. So it takes extra shielding to protect yourself from gamma. But finally, even before they put a sample in there, that Geiger counter, which is what was used to measure the radioactivity, that Geiger counter was measuring radioactivity even when there wasn't a beta or gamma sample in the sample holder there. And that just shows that there's radiation around us all the time. So our bodies are used to some radiation around us all the time. We just don't want to have an excess of radiation around us all the time. So when you're going to have a nuclear equation, it has to be balanced. And in effect, it's a pretty chill process, but you want to have reactant protons on the left equal the reactant protons on the right. You want the atomic numbers on the reactant side to equal the atomic numbers on the product side. And you have to do the same thing for neutrons. And remember, neutrons are kind of expressed through the mass number. So you want the mass numbers on the reactant side to equal the mass numbers on the product side. As an example of that, let's look at this radium-226 isotope that's decaying to an alpha particle, which is 4,2 helium, alpha particle, and a radon-222. And if you look at the upper left-hand numbers first, those are the mass numbers. 226 for the radium equals 4 plus 222 for the alpha and the radon. So that reaction is balanced for neutrons, and then the lower left-hand numbers also balance. So 88 is the number of protons for radium. That equals 2 for the alpha particle plus 86 for the radon. So notice that the numbers in the upper left have to equal the numbers on the upper left on the other side, and the same thing for the lower left. Those numbers also have to match on both sides. So it's not too hard to do. This is the kind of problem you might see, though, and it does help to know what those different particles are. So uranium-235 decomposes through beta decay to a new product. You can find the identity of the product. And in the upper right-hand corner there, I have the symbols of the different particles that we're looking at in this section. So beta particle is the second row under alpha particle there. And you can see that the beta particle is 0 minus 1e or 0 minus 1 beta. So in a problem like this, what I would do is first of all figure out what uranium-235 looks like. The 235 is the mass number, goes in the upper left corner. And uranium on the periodic table is number 92, so that means the lower left number is 92. So you will need a periodic table next to you unless you have the periodic table memorized, which is awesome too. But anyway, that uranium-235 then is essentially breaking down. And it's breaking down into a beta particle, 0 minus 1e or 0 minus 1 beta, either one is fine, and then something else. And for that something else, I'm just going to have a random AZX kind of symbolism there, where A is the mass number, Z is the atomic number, and X will be the symbol. So this is the equation that we have. We don't know what the missing particle is, but you can probably imagine it won't be too terribly hard to figure out. As an example, 92, the atomic number on uranium, that's going to equal minus 1 plus Z. The atomic numbers on the product side will solve for Z, then define that the number is 93, stuff like that. What we want to do, 235 on the top equals 0 plus A equals 235. All right, so that's not too crazy. 92 equals minus 1 plus Z. Solve for Z by adding 1 to both sides. Z is 93. Now to figure out X, you have to look at the periodic table, which element has 93 protons, and that's neptunium. So for this problem, the balanced reaction would look like that. You'd have uranium-235 breaking down to a beta particle, and you also have neptunium-235 as the other product. Cool. So that's kind of how this works. It's not too hard. What's really kind of interesting here, though, is that in reality, one of the neutrons in uranium is breaking down, and it's breaking down into a beta particle, 0 minus 1e, plus a proton. And if you look at the symbols for electron and proton and add them up, well, minus 1 plus 1 is 0, which is what the neutron has in the lower left. 0 plus 1 on the top equals 1 on the top, which is what neutron has. So that's the reason why electrons and beta particles have a negative 1, because electrons plus protons will equal a neutron, essentially. One of the neutrons in uranium-235 is breaking down, and it's breaking down into a beta particle and neptunium-235. Here's a reaction. It's a uranium-235, but it has a different decay. It's breaking down to a thorium-231 and some other mysterious product, and it wants to know what the unknown particle is. So in this problem, we'll do the same thing. All the numbers in the lower parts have to equal each other on both sides of the arrow. Same thing for the upper numbers. So for example, 235 equals 231 plus A. So A is going to be 4. And 92 on the bottom equals 90 plus Z. Z is going to equal 2. So we have 4 for A, 2 for Z. If you look at periodic table for number 2, 2 is helium. And a helium-4 is an alpha particle. So the complete reaction would look like this. Helium-4 is a product. It does help to know what helium is versus beta, stuff like that. So keep that in mind. If you hear about a reaction that undergoes emission or decay, whatever is being emitted or whatever the decay is, it implies a product particle. And as an example of that, here's a reaction with a positron emission. So again, look for emission and decays. This is a positron emission, so that means a positron, that 0 plus 1 beta, is going to be a product. So emission and decay, whatever is being emitted or decaying, it's going to be a product. This is a polonium-207 breaking down to a bismuth-207, and in the process, a positron comes off. Sometimes you see a capture. This is mostly used for neutron capture, but sometimes for electron capture as well. Whatever's being captured will be a reactant. So here's an example of a neutron capture reaction. Fluorine-19 can absorb a neutron essentially to make fluorine-20. So a neutron capture means that whatever is being captured is a reactant. The neutron here is a reactant, and you can figure out the other pieces from there. There's lots of types of particles and lots of types of decays. This just shows some random ones: alpha decay, beta decay, positron emission, electron capture, gamma emission, spontaneous fission. Focus on the first parts. Decays and emissions, again, are going to have a product, while capture will be a reactant. Gamma emission just means a gamma is being emitted, all right? And spontaneous fission is a little bit more complicated for what we need, but it basically is one piece breaking down to lots of smaller pieces. But the ones we can predict anyway, is just, cool scientists, will be the decay and the emission ones. Don't worry about the spontaneous fission. That would be pretty crazy. An unstable element usually decays through several steps until it gets to a radioactive or an isotope which is stable. And this shows the decay scheme for uranium-238, and it actually goes through 14 different steps before you finally get to stable lead-206. So all of those other isotopes listed on there are unstable until you get down to lead-206. So you'll see here that there's green arrows and there's red arrows. And the green arrows are basically having an alpha particle emitted, because you can see, like in the top there, that uranium-238 is going to a thorium-234. That means it's emitting an alpha particle. On the other hand, all of those red arrows, those are beta decay. So when a particle that's being emitted is an electron, and so in thorium-234 there, it's going to turn into 234 protactinium. That's PA, not Pennsylvania. Sorry, Pennsylvania. But anyway, that's an example of a beta decay, and that further decomposes into the very unstable uranium-234 before you start getting into alpha decay once again. So again, it's really crazy. People have studied this. They create elaborate pieces, but you could write the balanced reaction for all of these. All right, no problem. Alpha decay means it's kicking out an alpha particle. Beta decay means it's kicking out a beta particle. Now, this positron thing is really wild, all right? And Paul Dirac was actually the first person to predict antimatter back in the 1920s, and he thought it might be identical to regular matter except for its opposite charge. And positrons are the first example of antimatter that, as I know, were ever experienced. Positrons are anti-electrons. Now, when you have regular matter and its antimatter component next to each other, when they combine, it leads to what's called called annihilation, which is basically when gamma rays are emitted. And notice in that balanced reaction, the beta particle, the left-hand side, and the positron, the 0 plus 1e particle, when those two particles come together, they create two gamma rays. And that's very, very common. Two particles in create two gamma particles. Two gamma rays would be a better way to say it. There's something in symmetry and quantum chemistry we're not going to talk about, but that's why that happens. Pretty cool. But more interesting than not, up at OHSU, they actually use this. If you've ever had a PET scan, or you knew someone that did, PET, by the way, stands for positron emission tomography, they're essentially using antiparticles to create an energy spike that is detectable. Then they can search for your soft tissues and stuff. Anyway, it's really cool stuff, and there's practical uses. It's not just cool Star Trek things like I'm talking about, basically. Lots of examples of annihilation reactions. Here's the neutrino and an antineutrino. They combine as well to make two gammas. If you had a proton and an antiproton, they would combine to make two gamma radiation. Amazing. All right. Neutrino is another one of these subatomic particles that we're not going to talk about. Very cool kind of stuff. Anyway, go with the flow. Another type of system you might see in this kind of section would be a metastable nuclei. And if you have an electron in an atom and you excite it, it relaxes back down. And we saw back in Chem 221 that this is the basis of emission spectroscopy, and it's what's used for absorbance spectroscopy. And the wavelengths that come out are usually ultraviolet, infrared, visible, stuff like that. Well, the nucleus itself can be excited as well. So if the nucleus gets excited, it creates this metastable nuclei. And just like electrons, the nucleus can relax back to a ground state. But because everything in the nucleus is so high energy, a gamma ray is usually emitted. This is an example of a metastable nuclei reaction. And notice the little M there on the left-hand side. Tc is technetium. So they call the M-tet version of technetium, they call that metastable technetium. And what happens is when it relaxes back to regular technetium. So you can see the M is gone. And you also have a gamma ray. So the M just means it's metastable. It's an excited nucleus. You can think, if you will, that instead of having a nice distribution of protons and neutrons kind of mixed together, maybe you have a lot of protons on one side and a lot of neutrons on the other. So it's a very unstable kind of configuration. And it will decompose back to the regular version. In the process, a gamma ray is emitted. So again, there's no change to atomic numbers, no change to the mass numbers. You just have a gamma ray emitted. Medical imaging, also used at OHSU. This is a real common procedure, and you can have technetium, metastable technetium, made pretty readily. It decomposes to regular technetium, which further decomposes, if I remember, to molybdenum. So it's just something to think about. The medical applications of a lot of this stuff are quite fascinating. So it's more than just like cool science fiction stuff, and it is pretty cool science fiction stuff in my opinion. However, there are some real practical uses as well.